Okay, next video on sampling distribution. So now we're going to focus in on specific estimators. Our first statistic that we'll be talking about are our proportions. So in the chips example, we collected many samples of size 20 and calculated the sample proportion of red chips. How well does the sample proportion estimate the true proportion of red chips? So we're going to want to reflect on the last video where we said that for an unbiased estimator, we want to look for the true, your distribution being centered at the true proportion. So if our true proportion for a population is 0.5 and our graph is centered at least about 0.5, okay, that would make your proportion an unbiased estimator for your actual parameter value. And so in terms of using it to estimate your population, it would be a good estimator. So the first thing that I want to talk about is the idea that we're talking about binomial random variables here. So you may have caught on to that before, especially if you happen to do the reading, okay? But if you're thinking about the what we're looking for the proportions of successes from some sample of a population. So in the red chips example, you have a large population and you're looking for what is the proportion of red chips. So red chips would be your success right there, okay? And so because we should have started to notice that it is appearing that our sampling distributions for our proportion statistics look to be approximately normal as long as we have a large enough sample size. So we saw that in the first video that we started with the sample size of like 35 and then we moved it to 500 and either way it looked approximately normal. So if we wanted to use a normal model, we would definitely need to specify two parameters, our mean and our standard deviation. So back in chapter 16, we learned our mean and our standard deviation for a binomial random variable. So for our mean for our binomial random variable, we used this form. The number of trials times the probability of success. Okay. Of course, here we're dealing with a sample, not an entire population. So because you're dealing only with part of it or a fraction of it, we're going to take only a fraction of it. Okay. So we'll do 1 over n times the mean of the entire binomial random variable. What happens is when you multiply your ends drop out. So ultimately, the mean of your proportion for your sample is just going to be your proportion. Similar to that is the idea of your standard deviation. So your standard deviation for your binomial random variables was given to you as your number of trials times your probability of success times your probability of a fail. Okay, we are of course dealing with a small sample here, not an entire population, and so we are taking a fraction of your standard deviation for your binomial random variables. Going through the math on the slide, you will see that we ultimately end up with this as being what we will use to find the standard deviation of your sample proportion. If you do take a look at your reference sheets as well, these are both on there, so just know where to locate them, and we'll figure out how to use them in just a few moments. So what we're looking to kind of get to is the idea of, can we always use a normal model? So it will be ideal for us to use a normal model for our approximations for our samples. We can use a normal model as long as a few assumptions and or conditions are met. So we have to check three major ones. So the first one that we'll check, it's quite often assumed, but we need to check it regardless, would be the randomization condition. So if your sample came from an experiment, you need to make sure that the treatments were randomized, and they will tell you somehow. It's not anything that you'll necessarily be looking for. It will be worded somehow in your problem. If your sample came from a survey, you need to make sure that it is a simple random sample. If your sample came from some other type of method, make sure it is an unbiased and it is representative. The next thing that we need to check is for independence. The independence assumption is going to tell us that the individuals in the sample must be independent of each other. Sometimes it will just tell you that they are individual, but more than likely we will probably have to check for independence, and we will do that with the 10% condition. So you may assume independence if your sample is within 10% of the population. We did this when we during our while we were in binomial and geometric probabilities. So once you've sampled more than 10% of the population, it would not be considered independent. Okay, and if it's not, then you cannot use a normal model. So the way that we'll check that is by taking our sample size and seeing if it's less than or equal to 1/10 of our population. Okay? Sometimes you won't have your actual population. I'd say often you wouldn't have your actual population, but it would be easy to figure out if your sample is less than or equal to 10%.
Staff, if you're attending the staff meeting, please report to the theater at this time.
Sorry about that. So, so often you might just know that you're doing a random, you have a simple random sample of 200 women aged 18 to 30, and you are trying to find the proportion of the population. Well, I think it's safe to assume that 200 women aged from 18 to 30 is definitely within 10% of the entire population of women from 18 to 30. The last condition that we're going to check is known as the large counts condition. We have also talked about it, and we've referred to it as the success failure condition. So your sample size N, it must be large enough. The closer P is to 0 or 1, the larger N must be. So the sample size must be large enough that we will expect to see at least 10 successes and at least 10 failures. So we checked this when we were dealing with a binomial random variable that was approximately normal, or showed approximately normal distribution. We were allowed to use a normal model as long as our success failure condition was met. So we did that the same way that we're going to find if we can use it for these as well. So you're taking your sample size and multiplying it by your proportion, making sure that that is greater than or equal to 10. You're going to do the same thing with your sample size multiplied by the proportion of a fail, and make sure that that is at least 10 as well. So let's just take a look at a quick example. It's actually not quick at all because it's a long process, longer than you think it's going to be. So a polling organization asks an SRS of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students actually attend college within 50 miles of home. What is the probability that the random sample of 1,500 students will give you a result within 2 percentage points of this true value? So I think it's important to kind of realize right away that we're kind of looking, or what we're looking for. So we're going to be looking for the probability 2 percentage points of your 35%. Okay, so that's what we're actually looking for, okay? It would be nice to use a normal model, but we don't just assume. We must check the 3 conditions, okay? So we're checking our conditions for normal. Okay, the first one that I'm going to check is random, okay? They'll always tell you something in words where you can find it. So they do say that it was a random sample of 1,500, okay? So it seems almost pointless to check this because they'll tell you, but you do have to put that when you're checking your conditions. In order to use it, you need to check it. So a random sample, we're good. They say a random sample of 1,500. Okay. Or independence. Okay. So we can assume independence here because we would know that clearly 1,500 first-year college student is definitely less than or equal to the whole population of first-year students. Yeah, oh, definitely less than or equal to 10% of the population. And then finally, the large counts, okay, or your success failure condition. Okay. So we're looking for n times p to be greater than or equal to 10. Well, 1,500 times 35% is equal to 525, and so that's definitely less, greater than, sorry, I was thinking 10% condition first. It's definitely greater than or equal to 10. So you're good on your successes. Now just take a look at your fails. Make sure your fails are at least 10 as well. Okay, so we have 1,500 now times 0.65 would be your fail. So that's 975, which is definitely greater than or equal to 10. So you're good on your fails as well. So all of our conditions are met, and so we will be able to use a normal approximation for this, or a normal distribution. Give me 1 second. Okay, so I'm just going to continue this on a blank slide. So, just back to what we're looking for. Okay, so we're looking for within 2 percentage points of that 35% that they told us. Okay, so we of course would have to find our mean if we're going to use our a normal distribution. So we will do that. So that was the 1 times n, 1 over n times np, but then we saw that that was ultimately just equal to p. Okay, and then our standard deviation is also needed here. Okay, so we'll do that using the following form. So our success was 0.35, our fail 0.65, and our sample 1,500 will give us a standard deviation of 0.0123. Okay, so Now we're looking for a normal distribution with a mean of 0.35 and a standard deviation of 0.0123. Okay? So we would like to use our norm CDF function on our calculators, but remember that a sketch would be needed here. So I'll just do a quick sketch. Okay, here's my proportion, 0.35. I'm looking for within 2 percentage points of your proportion. Okay, so there's my sketch. And now I can continue with my math. So, okay, so I'm going to want to use my norm CDF function under your distor button on your calculator. Okay, it should command you, okay, your lower boundary here, your upper boundary is the 0.37, your mean at 0.35, and your standard deviation. Okay. This will give you about 89.6%. So in terms of how you would interpret this, what we can say is that about 89.6% of all simple random samples of size 1500 will give you a result within 2 percentage points of your true population, which is first-year college students within 50 miles of their home. That completes this video.